So we had a test accuracy of going up all the way to 95 with these settings for the best performance, but that's what we have at the moment. So why can't we reproduce the results? Yeah, we have the batch size of 64, epochs 30, initial learning rate, that, and augmentation false, shuffling true. I was getting 95% test accuracy with average training accuracy at almost 90%. So am I currently using the same settings? Just go step by step. The answer should be yes. So I achieved those higher scores, a higher performance, higher test accuracy with the following code. Can we go over it again? This is the previous version of the code that I'm using, and see what could be the reason for the difference in performance.
Both scripts use a batch size of 32 and an initial learning rate of 0.001, which should, in theory, provide similar results. However, the interaction between these parameters and the dataset can result in slight variations in performance, especially if the model converges differently during training. These parameters appear consistent, so the main difference in performance likely isn't directly due to these settings.
And now we have a different result again. It's the confusion matrix. Yeah, it's a bit worse actually overall. There are more false negatives. I think there's more false positives as well. And there's some examples of this true label is, so say, where it's clearly a seizure. I don't know, this one, that one. But the prediction says no seizure. So this is where it's going wrong. And same for those ones, it's actually not a seizure, but the model is labeling it as yes seizure. So it's a problem. So we're saving the results as of current time. Yeah, when we have the current settings stored, which is good. So we have all the output. It looks like a significant difference between the current performance and what we achieved in the past. Can we go over the details again in continuous sentences, full paragraphs, without any code? Just go over the conversation above.
Your current model performance shows a test accuracy of 81.67%, with an average training accuracy of 60.25%, and an average validation accuracy of 69.78%. This contrasts noticeably with your earlier results, where you achieved higher performance metrics, including a better test accuracy. Several factors could contribute to this difference in performance. From reviewing the previous code and discussions, it seems that the current model settings might not be fully optimized, or might differ slightly from those that previously led to higher accuracy. 1. Batch size and learning rate adjustments. The older code used different batch sizes and learning rates during various tests. Even though both the current and past models often used a batch size of 32 and a learning rate of 0.001, there were instances when a higher learning rate or different batch sizes were tested. These subtle changes can significantly influence how quickly or effectively the model converges, impacting final performance. 2. Augmentation and shuffling. Both versions used augmentation set to false and shuffling set to true. While these settings are consistent, shuffling introduces some inherent variability in how data is presented to the model across different epochs. Although the random seeds are set for reproducibility, slight differences in how data batches are shuffled and processed can still affect learning outcomes. Augmentation was kept off, likely to keep the training process straightforward, but revisiting augmentation could potentially boost performance by enhancing the model's generalizability. 3. Training and validation dynamics. The calculation of steps per epoch and validation steps directly influences the training cycle. In previous settings, slight modifications in how these values were handled could have led to better alignment between training and validation phases, indirectly boosting the performance metrics.
Commenting out the random seed and the random set seed seem to have improved the results slightly.
Commenting out the random seed settings, np.random.seed42 and tf.random.setSeed42 can indeed impact the performance of your model, sometimes leading to improved results as observed in your recent tests. Random seeds are used to ensure reproducibility, meaning that each time the code is run, the model's training process, data shuffling, and weight initialization occur in the same way. This consistency is often useful for debugging and comparing models under controlled conditions. However, when the random seeds are not set, each run will have a different random initialization of weights, data shuffling, and potentially other stochastic elements within the training process. This variability can sometimes lead to better model performance, as different random initializations can allow the model to find a more optimal solution during training. In your case, the test accuracy improved from 81.67% to 91.67%. And other metrics like average training and validation accuracy also increased significantly when the random seeds were not fixed. The observed improvement between the two runs suggests that the model benefited from a different initialization, which is a normal aspect of machine learning models that involve stochastic processes. The difference between the two runs is significant, as the test accuracy improvement is about 10%, which is substantial. The training and validation losses are also noticeably lower, indicating better learning and generalization of the model during training. The key takeaway here is that while setting random seeds helps with reproducibility, allowing some variability can sometimes help the model achieve better performance, especially when it comes to finding a more effective starting point for learning. It's worth noting, however, that the performance gain is not guaranteed and could also go in the opposite direction in other runs. Therefore, it's good practice to conduct multiple training runs and average the results to get a better understanding of the model's true performance.
Okay, I would like to evaluate the model and the results of it. So this is what we have for the most recent run, and this is the code that we are currently using. Note that we commented out the random seed settings, so we have better results with augmentation turned off and shuffling turned on. Also have better results with the specific initial learning rate. Yeah, we have the settings from the original study. Yeah, from memory, original paper at 15 epochs and 0.01. Yeah, they do mention augmentation and shuffling. If we can focus on settings or potentially change the model. Let's see how we go. It's taking a hand on my ear. Yeah, so showing improvements, but yeah, commented out the random seed settings. Potentially resulted in better results. We meant to not have any pre-processing to the dataset. Can we check the code? Okay, can we go over the normalization? Why are we actually doing this? What's wrong with the original range?